Welcome to our channel. We are so glad you found your way here. Let us help you fall asleep. Let's begin with the aurora. How the solar wind paints the night sky. Take a slow, colored, deep breath in and release it. Let the weight of the day fade away as we embark on an unhurried, atmospheric journey through the wonders of the cosmos. Your mind is quiet, the universe is vast, and we are ready to explore. Intricate and vibrant, the auroras manifest as ephemeral curtains of light across polar skies. This phenomenon emerges when charged particles from the solar wind collide with the Earth's magnetic field, creating a stunning display of colors. The interplay of these particles with atmospheric gases results in a spectrum ranging from greens to reds and purples, illuminating the night with a surreal glow. Within this region, varying conditions influence the intensity and shape of the display. Solar storms, for instance, can enhance the flow of particles, leading to more dramatic and widespread auroral activity. The interaction occurs primarily in the ionosphere, where altitude plays a critical role in determining the colors produced. Oxygen at higher elevations emits red and purple hues, while lower altitudes yield the more commonly observed green. Observing these light shows often evokes a sense of wonder, as the visual spectacle is not only beautiful, but also a reminder of the intricate relationship between the Earth and solar phenomena. Local weather conditions, such as clear skies and minimal light pollution, greatly enhance visibility, allowing more observers to appreciate this natural occurrence. In regions closer to the poles, auroras can be a frequent sight, serving as a captivating reminder of the dynamic processes at play within the cosmos. Throughout history, these luminous displays have inspired countless interpretations across cultures. Indigenous peoples in the Arctic regions viewed auroras as the spirits of their ancestors, offering guidance and protection. For the Sami, the light was a manifestation of the souls of the deceased, illuminating the night sky with messages from beyond. These interpretations fostered a deep reverence for the phenomenon, intertwining it with rituals and folklore. In ancient civilizations, luminescent arcs were often seen as omens. The Norse regarded them as the reflections of the Valkyrie's armor, guiding fallen warriors to Valhalla. In contrast, the ancient Greeks attributed them to the goddess of dawn, Eos, believing her presence heralded significant events. Explorers and scientists have documented auroras, attempting to unravel their mysteries. In the 17th century, astronomers began to link these lights to solar activity. This connection provided early glimpses into the intricate relationship between the Earth's atmosphere and solar winds. In more recent times, the fascination with auroras has transcended scientific investigation, becoming an emblem of nature's beauty. Their ethereal glow captivates observers, driving tourism to polar regions and inspiring art, literature, and music. The enduring allure of these phenomena underscores humanity's enduring quest to understand the universe and its many wonders. Charged particles emitted by the sun, known as the solar wind, travel through space at astonishing speeds. Upon reaching Earth, these particles interact with the planet's magnetic field and atmosphere, resulting in a breathtaking display of light. This interaction occurs primarily in the polar regions, where the magnetic field lines converge, allowing particles to penetrate the atmosphere more readily. As solar wind particles collide with gases such as oxygen and nitrogen, energy is transferred, causing these gases to emit light. The varying colors seen in auroras, from greens to reds and purples, can be attributed to the type of gas involved and the altitude at which these collisions occur. Oxygen at higher altitudes produces red auroras, while lower altitudes yield the more common green hues. The occurrence of auroras is cyclical, corresponding to the solar cycle, which spans approximately 11 years. During periods of solar maximum, the intensity and frequency of these displays increase, leading to more vivid and widespread auroras. Scientists utilize ground-based observations and satellite data to study these phenomena, gaining insights into the dynamics of the Sun-Earth interaction. This ongoing research not only enhances understanding of auroras, but also enriches knowledge of the solar system's behavior and the broader cosmic environment. The intricate relationship between solar activity and terrestrial phenomena continues to reveal the complexities of this celestial dance. The Sun serves as a critical source of energy, influencing atmospheric dynamics and weather patterns. Its radiant energy drives the processes that govern not only temperature, but also the movement of air masses. The solar radiation absorbed by the Earth's surface leads to the heating of land and water, which in turn generates convection currents within the atmosphere. These currents are responsible for the formation of weather systems, including cyclones and anticyclones, which dictate local climates across various regions. Solar activity, particularly in the form of sunspots and solar flares, can induce fluctuations in the amount of energy reaching the Earth. These fluctuations contribute to short-term variations in weather, as well as longer-term changes in climate. In addition, the interaction between the solar wind and the Earth's magnetic field creates phenomena such as geomagnetic storms, which can disrupt communication systems and impact satellite operations. In polar regions, the interplay of solar wind and atmospheric particles creates vibrant auroras, a dazzling display of light that serves as a reminder of this connection. These atmospheric manifestations not only illustrate the Sun's influence, but also provide valuable insights into the underlying mechanisms driving planetary atmospheres. Each auroral event encapsulates the effects of solar activity, revealing the delicate balance maintained between the Sun and the Earth's atmosphere. The solar wind comprises a stream of charged particles primarily originating from the Sun's outer layers, composed mainly of electrons and protons. It flows continuously into the solar system, carrying with it a variety of heavier ions. These particles travel at velocities ranging from 300 to 800 kilometers per second, depending on the conditions present on the Sun's surface. In this region of space, the influence of the Sun extends beyond mere illumination. It generates a magnetic field that interacts with the Earth's magnetosphere, creating a protective barrier against high-energy cosmic radiation. This interaction is critical in shaping the auroras, as charged particles collide with gases in the Earth's atmosphere, releasing energy in the form of light. The properties of the solar wind vary significantly, fluctuating in intensity and density, influenced by solar flares and coronal mass ejections. During periods of heightened solar activity, these disturbances can lead to more intense auroral displays. The interaction of the solar wind with the Earth's magnetic field can also induce geomagnetic storms, capable of affecting satellite communications and power grids. Analyzing the solar wind's characteristics allows scientists to better understand its effects on planetary atmospheres and contributes to the broader understanding of space weather phenomena, bridging the gap between the solar and terrestrial environments. The Sun's structure consists of several distinct layers, each playing a crucial role in its overall function. The innermost layer is the core, where nuclear fusion occurs. Temperatures reach approximately 15 million degrees Celsius, generating energy that radiates outward. This energy production is essential for the sun's stability and longevity. Surrounding the core is the radiative zone, where energy moves outwards through radiation. Photons emitted in this layer can take thousands of years to escape, undergoing countless interactions with particles as they move toward the surface. This gradual process highlights the complexity of energy transfer within the sun. The convective zone lies above the radiative zone, characterized by convection currents. Hot plasma rises to the surface, cools, and then sinks back down to be reheated. This movement contributes to the sun's magnetic field and influences solar activity, including sunspots and solar flares. At the outermost layer, the photosphere emits visible light, creating the familiar solar glow. Above this layer is the chromosphere, a thin region that glows with a reddish hue during solar eclipses. The corona, extending far into space, is the sun's outer atmosphere, with temperatures reaching millions of degrees. These layers work in unison to sustain the sun's life cycle and impact the surrounding solar system significantly. Solar flares represent moments of intense energy release on the sun's surface, resulting from the complex interactions of magnetic fields. These eruptions are capable of releasing vast amounts of radiation across the electromagnetic spectrum. When they occur, the energy can travel through space at the speed of light, reaching Earth in approximately 8 minutes. Upon arrival, the radiation can interfere with the planet's magnetic field, creating fluctuations that affect communication systems and navigation technologies. Satellites in orbit become particularly vulnerable during these events, as they find themselves exposed to heightened levels of radiation that can damage their electronic components. The impact of solar flares extends beyond technology. Increased solar activity can lead to spectacular displays of the Aurora borealis and Aurora australis, as charged particles collide with atmospheric gases. This interaction results in vibrant colors illuminating the night sky, a visual manifestation of the underlying solar processes. While solar flares can disrupt daily life on Earth, they are a natural part of the sun's behavior. Scientists continuously monitor solar activity to predict potential impacts, employing various instruments to assess the dynamics of the solar atmosphere. Understanding these phenomena is essential for mitigating risks and enhancing preparedness against the effects of solar eruptions on terrestrial systems. Coronal mass ejections, often referred to as CMEs, represent significant bursts of solar wind and magnetic fields rising above the solar corona, or being released into space. With each event, vast amounts of plasma, typically exceeding 1 billion tons, are propelled away from the sun at speeds that can reach up to 3,000 kilometers per second. This ejected material, when directed towards Earth, interacts with the planet's magnetic field, resulting in complex and varied effects. The journey of these charged particles across the void can take anywhere from approximately 15 to 72 hours, depending on their speed and the solar wind conditions. Upon arrival, they can induce geomagnetic storms, which may disrupt satellite operations, affect power grids, and even increase radiation exposure for astronauts in space. The potential for such outcomes underscores the importance of monitoring solar activity. In the upper atmosphere, these interactions often manifest as brilliant auroras, illuminating the polar regions in hues of green, pink, and violet. These light displays, while stunning, are a direct consequence of the intricate dynamics between the solar wind and Earth's magnetosphere. Understanding CMEs is crucial not only for predicting their occurrence, but also for safeguarding technology and infrastructures that are vital to modern life. Each CME serves as a reminder of the powerful forces at play in the universe. The interplanetary magnetic field, generated by the Sun's magnetic activity, plays a crucial role in shaping solar wind as it travels through space. This field stretches far beyond the Sun, extending into the vastness of the solar system, influencing the trajectory and behavior of charged particles. Interactions between the solar wind and this magnetic field create complex structures, such as streamers and bubbles, which can be observed in the heliosphere. Charged particles released from the solar surface encounter the interplanetary magnetic field, which acts as a guiding force. It organizes these particles into a continuous flow, dictating their paths as they traverse the void. Variations in the magnetic field can induce fluctuations in solar wind speed and density, leading to dynamic phenomena that affect planetary atmospheres and magnetic environments. When these charged particles collide with Earth's magnetic field, they can create stunning visual displays in the polar regions. The interaction generates currents in the atmosphere that excite gas molecules, resulting in the vibrant colors of the aurora. Observations reveal that these displays are not just confined to Earth. Other planets, such as Jupiter and Saturn, also exhibit their own forms of auroral activity, showcasing the universal influence of solar wind and the interplanetary magnetic field across the solar system. The protective barrier known as the magnetosphere plays a crucial role in safeguarding Earth from the relentless bombardment of solar wind and cosmic radiation formed by the planet's magnetic field. This region extends thousands of kilometers into space, creating a shield that deflects charged particles. Its structure is influenced by the solar wind, which compresses and shapes it, resulting in a dynamic environment that fluctuates with solar activity. Within this protective expanse, charged particles are trapped, forming radiation belts that encircle the planet. The inner belt, primarily composed of high-energy protons, exists alongside the outer belt, which contains electrons. These belts contribute to the overall energy dynamics of the magnetosphere, serving as a reservoir that occasionally interacts with the atmosphere. So, interactions between the magnetosphere and solar wind lead to phenomena such as geomagnetic storms, which can disrupt satellite communications and power systems on Earth. The Aurora borealis and Aurora australis emerge at high latitudes due to these interactions, where particles collide with atmospheric gases, producing vibrant displays of light. Vigilant monitoring of the magnetosphere reveals insights into both terrestrial and space weather patterns, guiding technology and infrastructure to ensure resilience against the unpredictable nature of solar activity. Understanding this shield highlights not only its importance, but also the delicate balance sustaining life on Earth. The interaction of solar wind with the magnetosphere generates a captivating display that permeates polar regions. Charged particles from the Sun, propelled through the vacuum of space, encounter the Earth's magnetic field, creating a complex interplay. This field stretches and distorts under the influence of these particles, forming a protective bubble that absorbs and deflects solar energy. When the solar wind is particularly strong, disturbances occur, leading to magnetic reconnection. This process releases energy that accelerates particles along magnetic field lines toward the poles. Upon entering the atmosphere, these high-energy particles collide with gas molecules, resulting in the vivid colors that characterize auroras. The spectrum ranges from deep greens to vivid pinks, depending on the type of gas involved and the altitude of the interaction. This phenomenon occurs predominantly during solar storms, when the sun's activity increases, resulting in heightened solar wind intensity. Such storms can disrupt communication systems and power grids, serving as a reminder of the dynamic relationship between the sun and Earth. The auroras themselves, while beautiful, are manifestations of these powerful forces at play. Observing them offers insight into the interactions that shape not only the night sky, but also the conditions that sustain life on the planet below. Thermoprecursors particles from the sun, primarily electrons and protons, traverse vast distances through the solar system, propelled by solar winds. These particles travel at speeds exceeding 400 kilometers per second, carrying with them energy and momentum vital for understanding their effects on Earth. Upon reaching the planet's magnetosphere, they encounter the magnetic field, which serves as a protective barrier against the relentless influx of solar radiation. This interaction results in a complex dance where some of these charged particles are deflected, while others spiral along the magnetic field lines toward the polar regions. Here, they collide with atmospheric gases, predominantly oxygen and nitrogen. The energy released during these collisions manifests as the vibrant colors of the aurora, painting the sky in hues of green, pink, and red. In this region, the altitude influences the colors observed. At higher elevations, the presence of nitrogen produces shades of purple and blue, while lower altitudes yield the familiar greens. Each display offers a glimpse into the turbulent relationship between the Sun and Earth's atmosphere. Understanding the dynamics of these charged particles remains crucial for predicting space weather and its potential impacts on technology and life on Earth. This ongoing research enhances our grasp of the interconnectedness of celestial phenomena and terrestrial systems. The Earth's magnetic field plays a crucial role in the formation of auroras. Acting as a protective barrier, it deflects charged particles emitted by the sun. In regions near the poles, where this magnetic field is weakest, these particles are allowed to penetrate the atmosphere. The interaction between these solar particles and atmospheric gases produces a spectacular light show as energy is released in the form of visible light. The dynamics of this field result in distinct auroral shapes and colors. Variations in particle energy levels contribute to the palette of hues observed, ranging from greens to reds and purples. Each color corresponds to different atmospheric gases reacting at varying altitudes. Oxygen at lower altitudes emits green, while at higher altitudes, it can produce red. Nitrogen contributes blue and purple shades, creating a complex visual experience that highlights the unique atmospheric characteristics of this region. Observations reveal that the intensity and frequency of these displays are closely tied to solar activity. Solar flares and coronal mass ejections can significantly enhance the influx of charged particles, leading to more vivid occurrences. Understanding the magnetic field's influence not only elucidates auroral phenomena, but also provides insight into broader geophysical processes, reinforcing the delicate balance within Earth's system. The relationship remains an area of ongoing study, revealing new layers of complexity in our planet's interaction with the cosmos. Geomagnetic storms serve as significant triggers for aurora activity, instigated by disturbances in Earth's magnetic field. These storms arise when solar wind encounters magnetic fields and energetic particles emitted by the sun. Following intense solar flares or coronal mass ejections, vast clouds of charged particles travel through space, often colliding with Earth's magnetosphere. The interaction of solar wind with this protective shield generate fluctuations in magnetic fields, leading to heightened geomagnetic activity. Regions near the poles become particularly susceptible as magnetic lines funnel particles towards the atmosphere. Upon entry, these particles collide with gas molecules, primarily oxygen and nitrogen, resulting in the stunning displays of color that characterize the auroras. Increased solar activity correlates with more frequent and intense geomagnetic storms, thereby enhancing the likelihood of auroral formations. These storms are classified by their magnitude, with the most severe causing disruptions to satellite communications and power grids on Earth. The science of understanding geomagnetic storms continues to evolve, with researchers employing advanced satellite technology to monitor solar activity. Observations reveal intricate patterns, shedding light on the dynamics of solar-terrestrial interactions. This ongoing research not only deepens comprehension of auroras but also informs broader studies on climate and atmospheric phenomena, enriching knowledge of our planet's place within the solar system. The distinction between aurora borealis and aurora australis lies primarily in their geographic locations. The former manifests in the northern hemisphere, predominantly around the Arctic region. This phenomenon is often visible in countries such as Norway, Canada, and Alaska, where they illuminate the night skies with ethereal greens, pinks, and purples. The shapes these lights take can vary, often appearing as arcs, rays, or dynamic curtains, driven by interactions between charged particles and the Earth's magnetic field. Contrastingly, Aurora australis graces the southern hemisphere, primarily observable near the Antarctic Circle. Regions such as Australia, New Zealand, and parts of South America occasionally witness this celestial display. The hues and forms of Aurora australis can mirror its northern counterpart, showcasing a similar palette of colors and patterns, influenced by the same solar wind phenomena. Both types serve as a reminder of the intricate dance between solar activity and Earth's magnetic shield. This shield acts as a protective barrier, channeling particles toward the polar regions, where they become visible as these stunning light displays. Their occurrence is not random, rather, it is a reflection of the solar cycle, an 11-year pattern of solar activity, which influences the frequency and intensity of these atmospheric spectacles. The interaction of photons with atmospheric gases is a fundamental process underpinning the creation of auroras. When charged particles from the solar wind collide with the Earth's magnetosphere, they accelerate towards the poles. Here, the atmosphere, rich in nitrogen and oxygen, becomes the stage for intricate interactions. Photons, which are particles of light, play a crucial role in this phenomenon. As high-energy electrons from the solar wind strike oxygen molecules at altitudes of approximately 100 kilometers, they excite these molecules. This excitement leads to the emission of light, creating the vibrant colors associated with auroras. Oxygen, when energized, emits light in shades of red and green, depending on the altitude of the interaction. Below 100 kilometers, red light predominates, while green light emerges from reactions occurring at lower altitudes. Nitrogen also contributes to this display. When it is excited, it can emit blue or purple hues, enhancing the overall visual experience. The distribution and concentration of these gases in the atmosphere influence the resulting colors and patterns seen above. The interplay between the solar wind's charged particles and the Earth's atmosphere results in a complex but orderly display of natural light, illuminating the night sky in a dynamic exhibition of atmospheric physics. Each occurrence serves as a reminder of the intricate relationship between the solar environment and terrestrial weather systems. The role of oxygen in auroral colors is fundamental, particularly in defining the hues that grace the night sky. When charged particles from the solar wind collide with oxygen atoms in the upper atmosphere, the resulting excitation leads to the emission of light. The most common color produced by this interaction is green, which manifests at altitudes around 100 kilometers. This vibrant hue is often the most visible to the human eye, casting an ethereal glow across vast expanses. At greater altitudes, approximately 200 kilometers, oxygen contributes to a different palette. Here, the emissions shift to shades of red, appearing more subtle yet equally captivating. This phenomenon arises from the energy levels involved in the collisions, dictating the specific wavelengths of light released. The interplay between different energy states allows for these variations, creating a complex visual experience. Further north, where the auroras often dance more dramatically, nitrogen also plays a critical role in the overall display. Its interactions lead to purples and blues, complementing the oxygen colors and enhancing the scene. Together, these elements weave a complex visual narrative, painting the sky in ways that reflect the underlying physics of our solar system. The dynamic interplay of these gases remains a testament to the intricate processes at work high above the Earth's surface. Nitrogen contributes significantly to the palette of colors observed in auroras. When solar wind particles collide with nitrogen molecules, the energy from these interactions excites the nitrogen atoms. As they return to their ground state, they emit light in various hues. The shades produced depend on the altitude at which these collisions occur. At lower altitudes, typically below 200 kilometers, the collisions often yield a vibrant red. This occurs when nitrogen ions release energy as they transition to a more stable state. At higher altitudes, above 200 kilometers, different reactions take place, leading to the production of blue and violet colors. The emission spectrum of nitrogen is responsible for this atmospheric artistry, manifesting in the vastness of the night sky. The presence of molecular nitrogen, coupled with the intensity and angle of the solar wind, influences the overall display. Variations in solar activity can enhance or diminish these colors. During periods of heightened solar storms, the frequency and intensity of these interactions increase, resulting in more vivid displays. This region of the atmosphere serves as a canvas, reflecting the complex dynamics of solar and terrestrial interactions. Each auroral display is a reminder of the constant dance between solar energy and the Earth's magnetic field, shaping the visual phenomena witnessed by those below. Altitude variations in auroras arise from the interaction of charged particles with the Earth's atmosphere at differing elevations. These interactions occur predominantly between 80 kilometers and 300 kilometers above the surface, where the density of atmospheric gases changes significantly. At higher altitudes, the thinner atmosphere allows particles to travel further, resulting in more expansive displays of light. The interplay of solar wind and Earth's magnetic field influences this vertical distribution. When solar particles collide with atoms and molecules in the atmosphere, the energy released manifests as light. Different gases emit distinct colors when excited. Oxygen, for instance, produces a greenish hue at lower altitudes, while higher altitudes yield red and purple shades due to nitrogen's involvement. Variations in solar activity also impact the altitude at which these interactions occur. During periods of heightened solar storms, the influx of energetic particles can lead to auroras appearing at lower altitudes. Conversely, quieter periods may result in displays occurring higher in the atmosphere. Geological location also plays a crucial role. Regions near the magnetic poles experience more frequent and intense auroral activity due to the funneling of solar particles along magnetic field lines. This phenomenon creates a spatial dynamic in which certain areas witness more vibrant displays than others, shaping the experience of this celestial event. The Nakia 5 specific locations on Earth provide optimal opportunities for experiencing auroras, largely influenced by their position relative to the magnetic poles. Regions within the Arctic Circle, particularly parts of Norway, Sweden, and Finland, serve as prime viewing grounds. The combination of dark skies, low light pollution, and favorable meteorological conditions enhances visibility, allowing observers to appreciate the full spectrum of colors. These northern latitudes experience long winter nights, further extending the duration of potential displays. Places such as Fairbanks in Alaska and Yellowknife in Canada have gained international recognition for their frequent auroral activity. Here, the clear air and minimal obstruction offer unobstructed views of the shimmering lights. Southern counterparts exist, although less frequently discussed. The southern auroras occur near Antarctica, with locations like Ushuaia in Argentina providing rare glimpses of this phenomenon. The unique geography of these areas, with their vast expanses of open land, contributes to the unobstructed vistas necessary for optimal observation. Earth's seasonality also plays a critical role, as the months from September to March tend to deliver heightened auroral activity. Wind patterns and solar cycles further influence these occurrences, making some years particularly fruitful for observers. Understanding these geographical and temporal factors allows for better planning. Seasonal variations significantly influence the frequency and intensity of auroras. During the winter months, regions closer to the poles experience longer hours of darkness, providing an extended window for auroral displays. The extended nights allow observers ample opportunity to witness these phenomena, often in spectacular form. Conversely, the summer months bring shorter nights and increased daylight, which diminishes visibility. The equinoxes also play a crucial role in auroral activity. Around March and September, solar wind interactions with the Earth's magnetic field tend to increase, leading to heightened auroral occurrences. This is attributed to the orientation of the Earth's magnetic field during these times, which allows solar particles to penetrate deeper into the atmosphere. As a result, these periods often yield some of the most brilliant displays. Geographically, locations within the auroral oval, a ring-shaped zone around the poles, witness the highest frequency of these light displays. In places such as northern Scandinavia, Canada, and Alaska, the likelihood of observing auroras increases dramatically during winter and equinox periods, while the solar cycle, which spans approximately 11 years, also influences auroral frequency. Seasonal and geographic factors remain paramount. Understanding these elements enhances the chances of experiencing one of nature's most magnificent displays, illuminating the night sky with ethereal light. The solar cycle, spanning approximately 11 years, serves as a fundamental framework for understanding solar activity. It is characterized by fluctuations in the number of sunspots, which act as indicators of magnetic activity on the sun's surface. These sunspots, appearing as dark patches, are regions of intense magnetic fields that can significantly influence solar emissions. During the solar maximum, an increase in sunspots corresponds with heightened solar activity, resulting in more frequent and intense solar flares and coronal mass ejections. This region of heightened activity leads to an increase in the solar wind, the stream of charged particles released into space. The interaction between this wind and Earth's magnetic field gives rise to the stunning auroras observed in polar regions. Conversely, the solar minimum marks a period of reduced sunspot numbers and diminished solar activity. During these times, auroral displays tend to be less frequent, although they can still occur under specific conditions. The cyclical nature of this phenomenon allows scientists to predict periods of increased auroral potential, providing opportunities for observation. Studying these cycles not only aids in forecasting auroral occurrences, but also enhances comprehension of the broader implications for space weather and its effects on technology and life on Earth. Understanding these patterns is crucial for grasping the intricate relationship between our planet and the Sun. Most space weather forecasting plays a pivotal role in predicting auroral displays, merging the complexities of solar activity with terrestrial effects. This process begins with the observation of solar phenomena, such as coronal mass ejections and solar flares, which release charged particles into the solar wind. It is the interaction of this wind with Earth's magnetic field that initiates the conditions for auroras. Numerous satellites monitor solar conditions in real time, providing vital data that informs models used in forecasting. When a significant solar event occurs, scientists analyze its trajectory and potential impact on the magnetosphere, which envelops the planet. This analysis allows for the prediction of when and where auroras may appear, guiding both scientific research and public interest. Wispayan Fofar's unant public interest. In this region of the atmosphere, the interplay between solar particles and atmospheric gases results in ethereal light displays. Models of geomagnetic activity help delineate the areas most likely to experience these phenomena, often aligning with high-latitude locations. Enhanced forecasting capabilities have transformed the ability to alert communities and travelers to impending auroras, ensuring that the splendor of these displays can be experienced by many far. The implications of accurate forecasting extend beyond mere aesthetics, impacting technology, aviation safety, and communication systems, showcasing the profound interconnectedness of our cosmic environment. Measuring aurora intensity requires precise tools and techniques to capture the intricate dance of particles in the Earth's atmosphere. Ground-based observatories employ all-sky cameras, enabling the monitoring of auroral activity across vast expanses of sky. These cameras capture high-resolution images, translating the ethereal glow into quantifiable data. By analyzing variations in brightness, researchers can ascertain the intensity and extent of each event. Satellite observations add another layer of understanding, with instruments designed to detect electromagnetic emissions across multiple wavelengths. The combination of ultraviolet and visible light data allows for a comprehensive analysis of auroral phenomena. These satellites, orbiting at altitudes above the atmosphere, provide a global perspective, revealing patterns that ground-based instruments might miss. Magnetometers also play a crucial role, measuring fluctuations in the Earth's magnetic field caused by charged particles from the solar wind. This data is essential for correlating solar activities with the resulting auroral displays. By integrating measurements from various tools, scientists can build models that predict auroral behavior with remarkable accuracy. The interplay of these instruments fosters a deeper understanding of the mechanisms driving auroras. Insights gained from such measurements enhance knowledge of space weather, contributing to advancements in technology and safety protocols in a world increasingly reliant on satellite systems. The interaction between climate change and the visibility of auroras presents a complex relationship. Alterations in the Earth's atmosphere resulting from increased greenhouse gas emissions, can influence local weather patterns, affecting the frequency of clear nights necessary for optimal aurora observation. In regions where cloud cover becomes more prevalent, opportunities to witness these natural light displays diminish, limiting access for both scientists and enthusiasts alike. Temperature fluctuations impact atmospheric composition, which in turn modifies the conditions under which auroras manifest. The presence of particulate matter can obscure sightlines, while changes in humidity levels may alter the brightness and clarity of the phenomena. These environmental shifts prompt scientists to explore the broader implications of climate dynamics on geomagnetic activity and auroral displays. In the Arctic regions, where auroras are most pronounced, warming temperatures have begun to reshape traditional weather patterns. Melting ice and thawing permafrost are indicative of broader climatic shifts that may inadvertently influence auroral frequency. Consequently, researchers are tasked with understanding how these changes interact with the solar activity cycle and its effects on the geomagnetic field. Continued examination of this intersection between climate change and auroras not only enriches our understanding of atmospheric science, but also underscores the intricate balance of natural systems that govern our planet and its celestial interactions. The study of auroras reveals a rich spectrum of phenomena observable across various wavelengths. Ultraviolet and X-ray emissions, often invisible to the naked eye, provide critical insights into the energetic processes at play. These regions emit light when charged particles collide with atmospheric gases, generating a cascade of reactions that illuminate the night sky. In the ultraviolet range, these emissions can indicate the density of the ionosphere and reveal the dynamics of solar-wind interactions. Observations in the X-ray spectrum illustrate the high-energy electrons that precipitate in the atmosphere, showcasing the direct impact of solar flares and coronal mass ejections. Visible light auroras, typically associated with greens and purples, emerge from lower-energy interactions and are the most commonly observed. The colors result from different gases. Oxygen at high altitudes yields red, while nitrogen contributes to blue hues. Infrared observations capture the thermal emissions and help scientists understand the atmospheric temperature variations associated with these phenomena. Each wavelength uncovers unique details, contributing to a comprehensive understanding of the auroral processes. This multispectral perspective enhances our appreciation for the complexities of Earth's magnetosphere and its ongoing dialogue with solar activity, illustrating the delicate interplay of forces that shape our planet's atmospheric conditions. Satellites play a pivotal role in advancing our comprehension of auroras. Equipped with sophisticated sensors, they collect data across various wavelengths, capturing the subtleties of these luminous phenomena. By observing the interactions between charged particles and Earth's magnetic field from above, these instruments provide invaluable insights into the dynamics of the auroral displays. Monitoring the solar wind, satellites measure its speed, density, and magnetic orientation, allowing scientists to predict auroral activity with greater accuracy. This real-time data is crucial as it informs researchers about impending geomagnetic storms caused by solar flares. These storms can significantly impact the intensity and frequency of auroras, transforming them into vivid light shows across the polar skies. Additionally, specialized satellites like the Polar Orbiting Environmental Satellites contribute to understanding the atmospheric conditions that foster auroras. They track fluctuations in temperature and pressure, revealing the underlying processes that influence these magnificent displays. The continuous stream of data from these orbital observatories creates a comprehensive portrait of auroral activity. This information enhances not only scientific knowledge, but also practical applications, such as improving communication systems and satellite operations that may be affected by geomagnetic disturbances. Through the synergy of satellite technology and space weather research, the intricacies of auroras are gradually unveiled, inviting further exploration into their enchanting nature. Ground-based observations serve as a fundamental aspect of auroral study. Equipped with specialized instruments, researchers gather data that complements satellite findings. Magnetometers, strategically positioned in polar regions, measure minute fluctuations in the Earth's magnetic field. These fluctuations provide insights into the pathways of charged particles and their interaction with the atmosphere. All sky cameras capture the expansive view of the night sky, documenting the aurora's movement and intensity. High-resolution images reveal the intricate structures within these luminous displays. Spectrometers analyze the light emitted by the auroras, allowing scientists to decipher the chemical composition and energy levels of the particles involved. Ground-based radar systems also play a pivotal role. They monitor the upper atmosphere, tracking the speed and density of particles that contribute to auroral phenomena. This data aids in understanding the dynamics of solar wind and its effects on the Earth's magnetosphere. Collaborative efforts between observatories enhance the scope of these observations. Networks of researchers share real-time data, creating a comprehensive picture of auroral activity. This information is invaluable for predicting future events and understanding their potential impacts on technology and communication systems. By employing these diverse tools, ground-based observations continue to enrich the understanding of auroras, blending technological advancement with the natural wonders of the universe. The interactions between auroras and human technology reveal a complex relationship that influences various systems. Satellites, crucial for global communication and navigation, are particularly vulnerable during intense geomagnetic storms, which can disrupt their functionality. These disturbances, caused by charged particles colliding with Earth's magnetic field, can lead to unexpected failures, affecting everything from GPS accuracy to satellite imagery. Sent to satellites, power grids are susceptible to geomagnetic-induced currents. When solar storms reach Earth, they can induce voltages that disrupt normal operations, potentially resulting in widespread power outages. Historical events, such as the Quebec blackout in 1989, underscore the tangible effects auroras can have on infrastructure. Telecommunications also face challenges during these solar events. High-frequency radio waves, essential for long-distance communication, can be absorbed by the ionosphere, leading to significant signal degradation. This disruption can hinder emergency services and everyday communication. Despite these impacts, the phenomena associated with auroras inspire advancements in technology. Researchers develop more resilient systems, aiming to mitigate the risks posed by solar activity. These innovations not only protect existing infrastructure, but also enhance the understanding of space weather, leading to better preparedness for future events. In this way, the study of auroras not only illuminates the night sky, but also deepens the connection between humanity and the cosmos. Radio communication relies heavily on the ionosphere, a region of the Earth's upper atmosphere where charged particles interact with solar radiation. Auroras play a vital role in this dynamic, influencing radio wave propagation. When solar wind collides with the Earth's magnetic field, it creates fluctuations in the ionosphere that can enhance or disrupt radio signals. These interactions are particularly pronounced during periods of heightened solar activity, such as solar storms. Such events can lead to increased ionization in the lower regions of the ionosphere. This alteration can enhance the transmission of radio waves over long distances, allowing signals to bounce off the ionized layers. Conversely, severe disturbances can result in signal degradation or loss, impacting communications across vast networks in remote regions where terrestrial communication infrastructure may be limited. This phenomenon proves especially beneficial. The ability to utilize the enhanced ionosphere can facilitate crucial communications for those in isolated areas, connecting them to broader networks. Observations of these interactions contribute to understanding the complex relationship between solar activity and terrestrial technology. By studying the mechanisms behind auroras, scientists can better predict their potential effects on radio communication. This knowledge not only supports technological advancements, but also fosters a profound awareness of the interconnectedness of space weather and human endeavors. The delicate interplay between auroras and power grids reveals significant vulnerabilities in modern infrastructure. Auroras arise from the interaction of solar wind with Earth's magnetic field, leading to geomagnetic storms that can induce electric currents in power lines. These currents can cause voltage fluctuations, potentially damaging transformers and disrupting electrical systems. Monitoring space weather is essential to mitigate such risks. Satellite data provides real-time insights into solar activity, allowing grid operators to prepare for impending geomagnetic storms. This foresight can lead to the implementation of protective measures, such as reducing power loads or temporarily shutting down specific components of the grid. The consequences of neglecting these warnings can be severe. In 1989, a geomagnetic storm caused widespread power outages in Quebec, affecting millions and highlighting the fragility of electrical systems. These events underscore the necessity for robust contingency planning and infrastructure resilience. Researchers continue to uncover the complexities of these interactions. Scientists are developing models to predict how different solar activities influence geomagnetic conditions on Earth. Understanding these dynamics is crucial for safeguarding not only power grids but also communication satellites, navigation systems, and other technologies that rely on stable space weather. The relationship between auroras and power grids serves as a reminder of humanity's dependence on natural phenomena, emphasizing the importance of ongoing research and preparedness. Witnessing an aurora evokes a profound psychological and emotional response in observers. The vibrant colors dancing across the night sky captivate the human spirit, igniting a sense of wonder that transcends the ordinary. These light displays provoke reflection on humanity's place within the vast universe, inviting introspection and connection to the cosmos. In this region, individuals often report feelings of tranquility and awe, as if the magnificence of the aurora fosters a deeper appreciation for nature's beauty. The interplay of greens, reds, and purples invokes an almost ethereal sensation, creating a shared experience that can strengthen bonds between those who witness it together. The sight serves as a reminder of the interconnectedness of life, sparking conversations about existence and the mysteries of the universe. Emotional responses vary, with some experiencing joy, while others may feel a sense of melancholy or nostalgia. This complexity reflects the aurora's ability to tap into personal memories and aspirations. Encounters with these luminous phenomena often become cherished moments, etched into the minds of observers. As the lights fade, the lingering impact prompts a desire to understand the science behind the spectacle, fostering curiosity and inspiring future generations to explore the intricacies of atmospheric physics and celestial phenomena. Throughout history, interpretations of these luminous displays have varied significantly across cultures. They have been viewed as omens, divine messages, or expressions of the gods' moods. Ancient civilizations often attributed great significance to the lights, seeing them as a connection between the earthly and the celestial. Norse mythology, for instance, described the auroras as the reflections of the shields and armor of the Valkyries, guiding fallen warriors to Valhalla. In other regions, indigenous peoples crafted rich folklore surrounding these phenomena. Some tribes viewed the lights as ancestral spirits playing in the sky, while others believed they were the souls of the departed dancing among the stars. Each narrative provided a cultural framework that intertwined their existence with the cosmos, reinforcing community bonds through shared beliefs and stories. Artistic representations have also evolved, capturing the ethereal quality of the auroras. Early artists depicted them in paintings and carvings, attempting to convey the wonder and mystery of these lights. Modern interpretations often explore their scientific underpinnings, while still embracing the inherent beauty of the display. Photographs and digital art strive to capture the breathtaking colors and movements, reflecting both the technical aspects and emotional resonance of this natural phenomenon. Through these expressions, the aurora continues to inspire creativity, bridging science and art across generations. The role of photography in documenting auroras has significantly enhanced the understanding and appreciation of these natural phenomena. Capturing the intricate patterns of light, photographers utilize long exposure techniques to reveal the hidden details of this atmospheric display. Each image serves as a record, allowing scientists to analyze the interactions between solar winds and the Earth's magnetic field. Technological advancements have further transformed this field. High-resolution cameras and specialized filters illuminate subtle hues that may go unnoticed by the naked eye. The resulting photographs not only preserve fleeting moments, but also contribute to ongoing research into the complexities of the ionosphere. These visual representations often evoke a sense of wonder, drawing in both the scientific community and the general public. Each photograph holds the power to communicate the dynamic processes occurring in the upper atmosphere, fostering a deeper appreciation for the planet's natural phenomena. In addition, photography has become a tool for education, helping to illustrate concepts such as geomagnetic storms and charged particle interactions. Workshops and exhibitions centered around auroras encourage collaboration between scientists and artists, promoting a shared narrative that celebrates the beauty and complexity of Earth's magnetosphere. This interplay between art and science continues to illuminate the ever-changing relationship between humanity and the cosmos. Folklore and mythology surrounding auroras reveal deep cultural connections to these ethereal phenomena. Across various civilizations, narratives emerge to explain their captivating presence in the night sky. In Norse mythology, they were believed to be the shimmering shields of the Valkyries, guiding fallen warriors to Valhalla. Their movements sparked tales of divine intervention, a celestial bridge between mortals and the gods. Indigenous peoples of North America viewed auroras as ancestral spirits or manifestations of animals, each color representing different emotions and messages from the past. The Inuit, for instance, saw them as the souls of the deceased playing a game of ball made from a walrus skull, a playful yet reverent interpretation of the natural spectacle. In contrast, ancient Chinese scholars regarded the lights as a sign of significant events, linking their appearance to the fortunes of the emperor. Such associations underscored the belief that these radiant displays were omens, foretelling prosperity or calamity. Across the globe, the awe inspired by these lights transcends scientific understanding, embedding itself in cultural consciousness. They become symbols woven into the fabric of human experience, bridging the gap between the tangible and the mystical. This shared reverence endures, guiding individuals to seek meaning in the vast expanse of the universe. The pursuit of these mesmerizing natural displays requires an understanding of specific conditions. Observers are often advised to venture far from artificial light sources, allowing the delicate colors to emerge unimpeded. Ideal locations include high latitudes, particularly within the auroral oval, a region encircling the magnetic poles where auroras are most frequently visible. Timing plays a crucial role in this endeavor. The winter months typically offer longer nights and clearer skies, increasing the likelihood of witnessing the phenomenon. Clear atmospheric conditions, devoid of clouds, enhance visibility, while a new moon provides optimal darkness, further showcasing the ethereal brilliance. Knowledge of solar activity enhances the experience. The 24-hour solar cycle influences the intensity of the solar wind, which in turn affects the auroras. Monitoring solar flares and coronal mass ejections can provide insights into upcoming displays, allowing enthusiasts to plan their observations accordingly. Preparation is essential. Warm clothing, proper equipment, and a comfortable location contribute to a more enjoyable experience. Cameras equipped with manual settings enable the capture of these fleeting moments, preserving their beauty long after the lights fade. Efforts to understand auroras have seen significant contributions from citizen scientists. Individuals motivated by curiosity and the desire to contribute to research. Communities across various regions have formed networks, sharing observations and data on auroral activity. These grassroots initiatives foster collaboration among enthusiasts, ensuring that sightings are reported in real time. Such collective efforts enhance the scientific understanding of the dynamics involved in auroral formations. Engagement in this field often involves utilizing simple tools such as smartphones or basic cameras, alongside apps designed to track solar activity. This technology empowers individuals to participate actively in research. Even in the absence of formal training, observations gathered from various geographic locations provide researchers with valuable data, helping to map auroral occurrences and analyze patterns. The integration of citizen science into aurora research has also led to the establishment of educational programs aimed at increasing awareness. Workshops and online platforms facilitate knowledge sharing among participants, illustrating the science behind these phenomena. The sense of community formed around shared interests strengthens the bond between science and the public, illuminating the importance of collaborative efforts in advancing atmospheric research. By fostering this connection, these communities not only contribute to scientific endeavors, but also cultivate a deeper appreciation for the natural world and its intricate processes. This cooperative spirit continues to illuminate the path for future explorations. Indigenous knowledge offers unique insights into the phenomenon of auroras, deeply rooted in cultural narratives and historical observations. For millennia, numerous indigenous communities have shared stories that encapsulate their understanding of these luminous displays. These narratives often reflect a profound connection to the natural world, revealing interpretations that go beyond mere observation. In various regions, the auroras are viewed as manifestations of ancestral spirits or celestial beings, bridging the earthly realm with the cosmos. This perspective enriches the scientific understanding of solar winds and magnetic fields, effectively intertwining empirical data with cultural significance. The intricate relationships formed between these communities and their environments enable a comprehensive approach to studying auroras. Observations passed down through generations provide invaluable context for contemporary research. This knowledge allows scientists to appreciate the patterns and behaviors of auroras beyond physical attributes, incorporating the emotional and spiritual dimensions that indigenous cultures emphasize Research initiatives increasingly recognize the value of these perspectives, fostering collaborations that honor traditional wisdom alongside scientific inquiry. By integrating indigenous knowledge systems with modern astrophysics, a more holistic understanding of auroras emerges. This synthesis not only enhances scientific discourse but also acknowledges the deep-rooted connections between humanity and the cosmos, underscoring the importance of diverse viewpoints in unraveling the mysteries of the universe. Technological advancements have significantly transformed the understanding of auroras, providing tools that illuminate their complex dynamics. Satellites equipped with advanced sensors now orbit Earth, continually monitoring solar activity and its interaction with the magnetosphere. These observations enable scientists to model the intricate processes that give rise to these luminous displays. Instruments like magnetometers and spectrometers analyze the electromagnetic fields and particles that converge at the poles, offering insights into the conditions that create the vivid colors of the auroras. Wahalas, ground-based observatories, have also evolved, employing high-resolution cameras and thermal imaging technology to capture real-time data from the Earth's surface. These facilities, positioned in optimal locations, enhance the ability to study auroral phenomena from various angles, contributing to a comprehensive understanding of their formation and behavior. With advancements in data processing, researchers can now analyze vast datasets with unprecedented speed, allowing for more accurate predictions of auroral events. Collaborative international efforts have further bolstered research capabilities. Networks of observatories share data, creating a global framework for understanding how solar winds impact different regions of the planet. This collective approach fosters a deeper comprehension of the aurora's role within the Earth's atmospheric systems, revealing how they serve as a window into the interactions between solar activity and our planet's magnetic field. Emerging technologies are poised to revolutionize the study of auroras, providing unprecedented insights into these atmospheric phenomena. Advanced imaging techniques, such as high-resolution cameras and spectrometers, allow for more detailed observations of auroral structures. These tools capture the intricate patterns of light emissions in real time, revealing the subtleties of the interactions taking place as solar winds collide with the Earth's atmosphere. Satellite missions equipped with sophisticated sensors are enhancing our understanding of the conditions that lead to auroral formation. Data collected from space offers a broader perspective, balancing ground-based observations with aerial views of the atmospheric dynamics. This dual approach enables scientists to analyze the solar wind's behavior as it approaches Earth and to predict auroral events with greater accuracy. Artificial intelligence and machine learning algorithms are becoming instrumental in processing vast amounts of data generated by these observations. They identify patterns and correlations that might elude human analysts, contributing to refinements in predictive models. Such advancements will, as these technologies evolve, the potential for interdisciplinary collaboration grows, integrating fields such as meteorology, astrophysics, and environmental science, all united in the pursuit of knowledge about this mesmerizing atmospheric occurrence. The interplay between auroras and atmospheric chemistry reveals a complex relationship that underscores the delicate balance within Earth's atmosphere. As charged particles from the solar wind interact with the gases in the upper atmosphere, their energy alters the chemical composition of this region. Nitrogen and oxygen molecules become excited, leading to the emission of light in various colors, manifesting as the ethereal glow that captivates observers. This phenomenon not only illuminates the sky but also affects atmospheric chemistry on a broader scale. The processes initiated by these interactions can influence ozone levels, as well as contribute to the understanding of how solar activity impacts weather patterns. The reactions occurring at high altitudes produce byproducts, which can lead to changes in the atmospheric composition, creating feedback loops that may influence climate. Research continues to uncover the subtleties of these interactions, demonstrating that variations in solar activity can have cascading effects on atmospheric dynamics. The study of auroras serves as a vital window into understanding the intricacies of atmospheric chemistry. Insights gained from these investigations enhance knowledge about the Earth's protective layers and the potential impacts of solar storms on satellite operations and communication systems. The intricate relationship between auroras and climate feedback loops emerges from ongoing research. Observations indicate that changes in solar activity can influence atmospheric conditions, which in turn may affect the frequency and intensity of auroras. This phenomenon involves the intricate interplay of charged particles from the Sun colliding with the Earth's magnetic field, resulting in the luminous displays that grace polar skies. Variations in solar output can lead to shifts in temperature and atmospheric circulation patterns. It is within these alterations that feedback loops can amplify or mitigate climate changes. Increased auroral activity, often associated with heightened solar wind events, may release energy into the upper atmosphere. This release can subsequently influence weather patterns at lower altitudes, creating a cascading effect through the climate system. Research has also highlighted that the changes in the ionosphere, driven by auroras, can impact radio wave propagation. This phenomenon further illustrates how interconnected these systems are, as alterations in communication capabilities can affect not only technology but also our understanding of environmental changes. Monitoring auroras provides critical data that can be correlated with terrestrial conditions. The insights gleaned from these observations hold the potential to deepen comprehension of complex climate dynamics. The polar regions present unique ecosystems intricately influenced by auroras. These phenomena, born from solar winds interacting with the Earth's magnetic field, create a stunning visual display that captivates both researchers and observers alike. In this region, where temperatures plunge and daylight wanes for months, life adapts to the harsh conditions, relying on the delicate balance between light and dark. Fluctuations in solar activity affect atmospheric chemistry, impacting plant life in ways that are not yet fully understood. Photosynthetic organisms, even in these frigid environments, utilize the limited sunlight available. The auroras play a role in altering the atmosphere, introducing changes that can promote or inhibit growth cycles within these ecosystems. The fauna, too, is affected by the rhythmic pulse of this celestial phenomenon. Species such as migratory birds and marine mammals navigate using natural light cues, which may be altered during intense auroral events. Behavioral patterns shift as these animals respond to the changing landscape, dictated by the interplay of electromagnetic forces. Research into the polar regions reveals a symbiotic relationship between these ecosystems and the auroras. As solar winds continue their journey towards Earth, the implications of these interactions become increasingly significant, offering a glimpse into the delicate threads that weave together life in the most extreme environments. The presence of auroras influences the behavior of various animal species, revealing a profound connection between celestial phenomena and terrestrial life. Many creatures, particularly migratory birds, rely heavily on natural light cues to navigate their long journeys. The ethereal glow of auroras can disrupt these navigational aids, leading to confusion and disorientation. Birds may stray from their intended paths, drawn towards the vibrant colors that dance across the sky, altering their migration routes and quista. Marine life also exhibits changes in behavior in response to auroral activities. Certain fish species are known to alter their feeding patterns during intense displays, possibly due to increased visibility at night. This shift affects predator-prey dynamics within aquatic environments, demonstrating the interconnectedness of life forms under the influence of atmospheric events. Terrestrial mammals, such as reindeer, exhibit heightened alertness during auroral displays, This species, which depends on the interplay of light and shadow for foraging, may become more vigilant as the landscape transforms under the shimmering skies. The profound impact on their behavior underscores the role of auroras as both a source of wonder and a factor in survival strategies. These atmospheric phenomena serve as a reminder of the delicate balance that exists within ecosystems, illustrating how celestial forces shape life on Earth in unexpected ways. The influence of auroras extends beyond terrestrial life, significantly affecting the realm of space exploration. These luminous displays indicate the complex interplay between solar activity and the Earth's magnetosphere, serving as an essential marker for scientists studying the planet's atmospheric dynamics. The presence of auroras signals heightened solar-wind interactions, prompting researchers to closely monitor these events for insights into magnetic field fluctuations. Auroras provide a natural laboratory for understanding charged particles' behavior, which is critical for the safety of satellites and crewed missions in orbit. The energetic conditions associated with these phenomena can lead to increased radiation exposure in space. Awareness of auroral activity allows mission planners to adjust trajectories and schedules, ensuring the safety of astronauts and equipment. This region of the atmosphere often acts as an interface between Earth and the cosmos, showcasing the striking effects of solar storms. Changes in intensity and frequency of auroras correlate with solar cycles, offering valuable data for predicting space weather. Such predictions are paramount, as they can influence communication systems, navigation, and power grids across vast distances. The study of these radiant displays extends beyond Earth, revealing a rich tapestry of auroras across various celestial bodies. Gas giants, such as Jupiter and Saturn, showcase auroras that far exceed those witnessed on our planet. These immense storms emerge from complex magnetic fields, interacting with charged particles in their atmospheres. On Jupiter, the auroras can reach altitudes of over 1,000 kilometers, presenting a vibrant contrast of colors against the dark backdrop of space. Saturn's auroras exhibit a unique characteristic. They are influenced by the planet's rotation and the solar wind's intensity. This region generates light that can flicker in brilliant hues, sculpted by the intricate dynamics of its magnetic field. It remains a subject of ongoing research, as scientists seek to understand the underlying mechanisms that drive these phenomena. Mars, in contrast, offers a more subdued display, lacking a global magnetic field. It experiences localized auroras, primarily near the planet's crustal magnetic fields. These events, while smaller in scale, provide essential insights into the Martian atmosphere and its interaction with solar radiations. The comparative analysis of auroras across these diverse environments enhances our understanding of planetary atmospheres and magnetic interactions. Each celestial body presents a unique canvas, shaped by its individual characteristics and the solar wind's influence. The magnetic field of other celestial bodies plays a pivotal role in shaping their auroras. In particular, planets like Jupiter and Saturn exhibit auroras that are both striking and complex. These massive gas giants possess strong magnetic fields, which are generated by the movement of electrically conductive materials within their interiors. The interaction between solar wind particles and these fields creates magnificent displays of light. On Jupiter, auroras can extend over thousands of kilometers, with colors ranging from deep blues to brilliant reds. Compared to Earth, the auroral phenomena on these giants are influenced by their unique atmospheric compositions. The presence of various gases alters the wavelengths of light emitted during these interactions. In Saturn's case, its auroras are often associated with its rings, which contribute to the processes that energize the particles involved. These structures not only influence the visuals but also affect the dynamics of the surrounding magnetosphere. Mars, a lacking a substantial magnetic field, experiences a different relationship with solar wind. Although it does not produce classical auroras, researchers have identified localized patches of atmospheric activity, regions where solar particles interact with the remnants of its magnetic field. This subdued response underscores the delicate balance between stellar interactions and planetary characteristics. Each observation enriches our understanding of auroras across the solar system. The study of auroras in outer solar system bodies reveals the diverse interactions between solar winds and planetary magnetospheres. It is within these distant realms that unique phenomena emerge, illuminating the skies of gas giants and icy moons. Jupiter, with its immense magnetic field, showcases auroras that are more than 1,000 times stronger than those found on Earth. This region experiences continuous bombardment from charged particles, leading to spectacular displays that are simultaneously mesmerizing and scientifically significant. Saturn presents its own form of intrigue. The planet's auroras are influenced by its rotation and the composition of its rings, creating a complex interplay of light that shifts and evolves. Observations from spacecraft have documented these luminous phenomena, providing insights into the underlying magnetic field dynamics and atmospheric conditions. In the case of Uranus and Neptune, the irregularities of their magnetic fields result in auroras that behave unpredictably. These distant planets possess unique atmospheric compositions that influence how energy is released, resulting in unusual spectral emissions. The study of these emissions allows scientists to better understand the processes that govern auroral activity in environments far removed from the familiar confines of Earth. Through meticulous observation and analysis, these auroras serve as beacons, guiding researchers towards deeper comprehension of planetary atmospheres and magnetic interactions across the solar system. Auroras on distant exoplanets reveal critical insights into their atmospheres and magnetic fields. By examining the light emitted during these events, scientists can infer vital information about the composition and dynamics of alien worlds. This phenomenon occurs when charged particles from stellar winds collide with atmospheric gases, creating vivid displays. Such interactions provide clues about the strength and structure of a planet's magnetic field, which is essential for understanding its capability to shield itself from harmful cosmic radiation. Research into the auroras of exoplanets offers an opportunity to explore the potential habitability of these distant realms. The presence of a magnetic field, indicated by auroral activity, suggests a protective barrier against solar and cosmic radiation. This protection is crucial for maintaining stable atmospheres that could support liquid water, a fundamental ingredient for life as known on Earth. Observations of auroras have been conducted using powerful telescopes and space-based instruments, allowing researchers to detect the faint emissions from light years away. These studies not only enhance knowledge of individual planets, but also contribute to the broader understanding of planetary systems and their formation. Thus, the role of auroras extends beyond mere illumination, acting as a gateway to unraveling the mysteries of cosmic environments and the conditions that may foster life beyond Earth. Artistic interpretations of auroras have emerged as a profound reflection of the natural phenomenon's ethereal beauty. Various creative endeavors draw inspiration from the vivid colors and dynamic movements observed in the night sky. Artists often strive to capture the delicate interplay of light and shadow, transforming celestial observations into visual expressions. These manifestations range from paintings and photography to installations that evoke the serene yet powerful presence of auroras. Scientific inquiry also finds its place within this creative landscape. Collaborations between artists and scientists have produced innovative projects that merge aesthetic experience with empirical understanding. Through such partnerships, the intricate data regarding solar winds and magnetic fields can be reimagined, enabling a broader audience to engage with complex concepts. These projects serve to bridge the gap between analytical study and emotional resonance, inviting contemplation of the cosmos. Exhibitions featuring auroral art can often include real-time data visualizations of belidistobria, allowing viewers to experience the live fluctuations of solar activity alongside artistic representations. The integration of technology into these displays enhances the connection between the observable universe and human creativity. Through this synthesis, a deeper appreciation for the aurora's role in both science and art emerges, highlighting the profound impact of these natural phenomena on our understanding of the world and the cosmos beyond. Auroral substorms represent a fascinating aspect of the auroral phenomenon. These localized disturbances in the Earth's magnetosphere manifest as sudden intensifications of the aurora, often characterized by bright, dynamic displays triggered by interactions between the solar wind and the Earth's magnetic field. They typically occur during periods of enhanced solar activity. This region becomes a canvas where charged particles collide with atmospheric gases, resulting in bursts of light that can shift in color and intensity. They usually unfold over the course of several minutes, sometimes lasting for hours. Initial phases may see the aurora dimming before a rapid brightening transforms the sky into a vivid spectacle. The palette ranges from greens to reds and purples, each hue a consequence of different gases and their respective altitudes. The energy released during these events can be significant, leading to the acceleration of particles along magnetic field lines. Research into these substorms sheds light on the underlying processes of magnetospheric dynamics. Their unpredictability provides insights into the complexities of solar-terrestrial interactions, while they can disrupt satellite communications and power grids. These disturbances also enhance our understanding of space weather. The study of auroral substorms continues to reveal the intricate relationships between solar activity and terrestrial phenomena, deepening knowledge of both Earth and the solar system. Geophysical instruments play a pivotal role in understanding the complexities of auroras. Ground-based observatories and satellites provide invaluable data about solar wind interactions with the Earth's magnetic field. These instruments measure variations in magnetic fields, electric currents, and atmospheric conditions, contributing to a comprehensive picture of auroral dynamics. Ground installations, such as magnetometers, monitor fluctuations in geomagnetic activity. These readings offer insights into the intensity and frequency of substorms, VAS, allowing researchers to connect solar events with observable auroral displays. The data gathered informs models that predict how solar particles will interact with the atmosphere, enhancing comprehension of the phenomena's scale and impact. Satellites equipped with advanced imaging technology capture the breathtaking colors and shapes of auroras from above. Observations from these vantage points reveal the extent of auroral activity, mapping the distribution of emissions across vast geographic areas. This aerial perspective aids in identifying patterns associated with solar cycles and their effects on Earth's magnetosphere. Radio wave instruments contribute to this understanding by detecting the natural radio emissions produced during auroral events. These emissions, generated by interactions between energetic particles and the atmosphere, provide a unique window into the underlying processes driving auroral formation. Together, these instruments foster an intricate understanding of the auroral phenomenon, bridging the gap between solar activity and Earth's atmospheric responses. Historical accounts of auroras can be traced back thousands of years, with ancient civilizations documenting their observations in texts and artifacts. Early records, often steeped in mysticism, describe these luminous displays as celestial omens or messages from the gods. Cultures across the globe, from the Inuit in the Arctic to indigenous tribes in North America, interpreted the flickering lights in diverse ways, often attributing them to the spirits of ancestors or other supernatural forces. As humanity progressed, so too did the understanding of these phenomena. The first scientific descriptions emerged during the Renaissance, where scholars began to correlate auroras with solar activity. Observational records from this period laid the groundwork for future study, fostering a more empirical approach to the enigmatic lights. With advancements in technology, modern data collection has transformed our understanding. Satellites equipped with sophisticated sensors now monitor solar wind and magnetic field variations, allowing researchers to decode the complex interactions leading to these displays. The transition from folklore to scientific inquiry reflects not only an evolution in understanding, but also the growing recognition of the interconnectedness between solar dynamics and Earth's atmospheric behavior. This ongoing exploration continues to enhance our appreciation for the aurora, revealing the intricate dance of particles that illuminates the night sky. Aurora activity holds implications that extend beyond the confines of the polar regions. Variations in its intensity can exert influence on global climate patterns, a phenomenon that has been the subject of scientific inquiry. These luminous displays arise from interactions between charged particles from the Sun and the Earth's magnetic field. When solar winds intensify, they can disrupt the magnetosphere, leading to heightened auroral activity. This in turn affects atmospheric dynamics. Changes in the upper atmosphere instigated by auroras can have cascading effects on weather systems. The additional energy introduced into the atmosphere can alter jet streams, creating shifts in temperature and precipitation patterns across vast distances. This region, characterized by its fluctuating conditions, can experience altered storm trajectories, which may impact agriculture and ecosystems far removed from the poles. Research indicates that these phenomena may also influence long-term climate trends. The solar cycle, which spans approximately 11 years, correlates with variations in auroral frequency. Understanding these cycles is crucial for predicting potential climate changes. The interplay between solar activity and Earth's atmospheric conditions illustrates a complex relationship, one that scientists continue to unravel. The significance of auroras extends beyond their visual allure, providing insights into the interconnectedness of solar phenomena and terrestrial climate systems. Auroras serve as key indicators of space weather events, offering a glimpse into the complex interactions between the solar wind and the Earth's magnetic field. These luminous displays arise when charged particles, propelled by solar activity, collide with gases in the upper atmosphere. This process illuminates the night sky in vibrant hues, revealing the influence of solar flares and coronal mass ejections. Regions situated near the poles experience these phenomena more intensely due to their proximity to the magnetic field lines. During heightened solar activity, the frequency and intensity of auroras increase, correlating with solar cycles. These cycles, averaging 11 years, dictate the ebb and flow of solar radiation and magnetic disruptions. The glow emanating from these atmospheric interactions serves not only as a natural spectacle, but also as a critical tool for scientists monitoring space weather. Through analysis of auroral patterns, researchers can predict potential disruptions to satellite communications and power grids on Earth. Data collected from ground-based observatories and satellites contribute to understanding these events, facilitating accurate forecasts. The implications extend to aviation, where flight paths may be adjusted to minimize exposure to heightened radiation levels. This ongoing research underscores the importance of auroras as both a beautiful phenomenon and a vital component of space weather monitoring. Solar activity directly influences the frequency and intensity of auroras. During periods of heightened solar activity, such as solar flares and coronal mass ejections, charged particles are released into the solar wind. These particles travel along magnetic field lines and interact with Earth's magnetosphere. The resulting disturbances can significantly enhance auroral displays, leading to more frequent sightings at lower latitudes than usual. This relationship between solar cycles and auroral occurrences is well documented. The 11-year solar cycle, characterized by varying sunspot activity, dictates the intensity of solar emissions during the solar maximum. The increased number of sunspots correlates with more frequent and vivid auroras. Conversely, during the solar minimum, auroras become less frequent, often limited to polar regions. Data collected from various satellites and ground-based observatories reveal patterns in auroral frequency that align with solar activity peaks and troughs. These observations contribute to predictive models that help scientists anticipate auroral events, enhancing our understanding of their dynamics. The consequences of solar activity extend beyond visual phenomena. Variations in auroral frequency can influence technological systems on Earth, including satellite operations and communication networks, highlighting the interconnectedness of these cosmic processes. Thus, the study of auroras serves as a vital link to both solar dynamics and terrestrial implications. The implications of auroras extend beyond their breathtaking displays, influencing modern navigation systems in profound ways. This phenomenon is closely tied to the interactions between charged particles emitted from the Sun and the Earth's magnetic field. When these particles collide with atmospheric gases, they generate light and energy, creating the dazzling visuals that captivate observers. However, this interaction can also disrupt the delicate balance of navigational technologies. Global positioning system signals are particularly vulnerable to these disturbances. They rely on satellites that orbit the Earth, transmitting data to ground receivers. When solar winds induce geomagnetic storms, the resulting fluctuations can alter the accuracy of these signals, leading to position errors. This effect is more pronounced in polar regions, where the density of charged particles is heightened. The reliability of navigation systems diminishes, impacting aviation, maritime routes, and even personal navigation devices. Telecommunications experience similar challenges. Radio waves utilized for communication can be refracted by the increased ionization in the atmosphere, leading to disrupted transmissions or loss of signal altogether. These disruptions can result in delays and miscommunications, emphasizing the need for continuous monitoring of solar activity. Understanding how auroras influence these systems is crucial for maintaining the integrity of our interconnected world. As solar activity continues to fluctuate, vigilance remains paramount. The unique interplay between solar winds and atmospheric phenomena shapes the ecology of regions with frequent auroras. In polar environments, where the auroras are most visible, organisms have adapted to thrive under these ethereal light displays. The presence of these lights indicates a high level of geomagnetic activity, often seen during solar storms, which influences local weather patterns and habitats. This region supports a diverse array of wildlife, including migratory birds and various mammal species. These creatures have evolved behavioral patterns that align with the seasonal changes marked by the auroras. The interplay of light affects feeding and breeding cycles, as the heightened solar energy can influence insect populations, a critical food source for many animals. Vegetation also finds ways to adapt to this unique environment. Lichens and mosses are prevalent, their growth patterns responding to the ambient light conditions created by these auroras. The spectral colors illuminating the landscape may enhance photosynthesis during certain times of the year, allowing these hardy plants to flourish in otherwise harsh conditions. Human inhabitants in these regions often engage with this natural phenomenon, culturally and socially integrating the auroras into their lives. It becomes a shared experience, an essential part of the identity of those who call this stark yet beautiful environment home. Historical accounts reveal notable auroral events that have captivated human observation for centuries. The year 1881 showcased an extraordinary display over North America. Vast waves of color engulfed the night sky, visible as far south as the Gulf of Mexico. Witnesses described the phenomenon as a dance of hues illuminating the landscape and igniting a sense of wonder among observers. Reports indicated that this event inspired local folklore, with communities attributing the sight to otherworldly forces. Another significant occurrence unfolded in the year 1903, when observers in Europe were met with a brilliant aurora, its glow reflected on the surface of the sea. This event was especially notable due to its alignment with solar activity. Scientific observations recorded heightened solar storms that contributed to the intensity of the auroral display. Such correlations deepened the understanding of the connection between solar phenomena and terrestrial experiences. In more recent history, the aurora borealis of the winter 2003 captured the attention of thousands across the northern hemisphere. The vivid colors were attributed to a massive coronal mass ejection, sending charged particles hurtling toward Earth. This event served as a reminder of the dynamic interactions between the sun and the planet, illuminating the night sky in a breathtaking spectacle that continues to inspire awe and curiosity. This phenomenon has given rise to a burgeoning industry dedicated to aurora tourism. Regions positioned under the auroral oval experience significant economic benefits as travelers flock to witness this celestial display. Local businesses flourish, catering to the influx of visitors seeking accommodations, guided tours, and unique experiences centered around the northern lights. Communities often organize events, festivals, and educational programs aimed at enhancing the visitor experience. These initiatives provide a platform not only for cultural exchange, but also for the preservation of local traditions and stories woven into the folklore surrounding the auroras. The economic stimulus extends beyond immediate tourism revenue. It fosters job creation in hospitality, transportation, and local artisanship. Environmental sustainability becomes paramount as communities balance tourism growth with the protection of their natural landscapes. Efforts to minimize light pollution and maintain the integrity of natural habitats ensure that the aurora remains not only a source of wonder, but also a vital ecological asset. Regional investments in infrastructure, such as improved roads and enhanced communication networks, cater to both tourists and residents. The synergy of economic development and environmental stewardship defines the evolving relationship between these regions and the auroras above, creating a resilient framework for future generations. The interplay of culture, economy, and nature continues to shape narratives centered on this remarkable atmospheric event. Auroras manifest as a direct result of complex interactions between solar winds and Earth's magnetic field. Charged particles emitted from the sun travel through the vastness of space, encountering Earth's protective magnetosphere. Upon entering this region, these particles collide with gases in the atmosphere, predominantly oxygen and nitrogen, at altitudes ranging from 100 kilometers to 300 kilometers. This interaction excites the gas molecules, leading them to emit light in vivid colors. The colors displayed in this phenomenon vary, with greens being the most common, resulting from oxygen at lower altitudes. Higher altitudes can produce reds, while nitrogen can yield blues and purples. This intricate dance of particles and gases creates a visual spectacle that is both ephemeral and awe-inspiring. Geographic proximity to the poles enhances visibility, as it is in these regions where the magnetic field lines converge. Auroras are not limited to their aesthetic beauty. They serve as indicators of solar activity. When solar storms intensify, they can lead to more pronounced displays. This connection between solar emissions and atmospheric reactions provides insight into both solar behavior and Earth's magnetic environment. Understanding these relationships deepens appreciation for the delicate balance governing the planet and its celestial neighbor, highlighting the intricate dance of forces at play in the cosmos. Education serves as a crucial mechanism for fostering awareness about auroras and their underlying phenomena. Engaging curricula that encompass atmospheric science and solar physics can illuminate the interplay between solar winds and Earth's magnetic field. Such programs equip learners with the knowledge to comprehend how charged particles from the sun interact with the planet's atmosphere, resulting in vibrant displays of light. Outreach initiatives often target schools and communities, encouraging curiosity and exploration. Workshops and interactive demonstrations facilitate first-hand experiences with concepts such as geomagnetic storms and ionization. These experiences enhance understanding and stimulate interest in scientific inquiry. Collaborative projects between educational institutions and research organizations can further amplify the dissemination of knowledge, resulting in informed communities. Public lectures and planetarium shows serve as additional avenues for sharing information. These events allow experts to convey complex ideas in an accessible manner, making the phenomena more relatable. Social media platforms also play a vital role, allowing for the rapid sharing of auroral forecasts and educational content. As a result, a broader audience can appreciate the beauty and significance of auroras. Increased awareness encourages responsible viewing practices, promoting respect for natural phenomena. This understanding cultivates a deeper connection to the environment, inspiring future generations to explore science and its implications for Earth and beyond. The future of auroras hinges on ongoing advancements in solar physics and magnetospheric research. Enhanced predictive models are being developed to better anticipate solar storms, offering insights into their potential impacts on Earth's magnetosphere. Scientists are now capable of analyzing solar wind patterns with unprecedented accuracy, employing satellite data to assess solar activity in real time. These observations contribute to a comprehensive understanding of how auroras will manifest under varying solar conditions. Climate change also plays a role in auroral phenomena. As the planet's atmosphere continues to warm, alterations in atmospheric composition may influence how these light displays interact with Earth's magnetic field. Projections suggest that a changing climate could lead to shifts in auroral intensity and frequency, potentially allowing these phenomena to be visible in regions previously unaffected. Furthermore, the expansion of commercial space travel could offer new opportunities for auroral observation. Spacecraft may facilitate enhanced viewing experiences, allowing individuals to witness these natural wonders from unique celestial vantage points. As humanity ventures further into space, understanding the aurora's role in the broader context of astrophysical processes becomes ever more crucial. These developments promise to illuminate not only the majestic beauty of auroras, but also their significance in the complex interplay between solar dynamics and planetary systems. The significance of auroras extends far beyond their visual splendor. They serve as critical indicators of solar activity, providing valuable insights into the behavior of the Sun and its interactions with planetary atmospheres. Each shimmering wave of color corresponds to charged particles colliding with gases in a planet's magnetosphere, revealing the intricacies of magnetic field strength and configurations. This phenomena facilitates a deeper understanding of how solar winds influence atmospheric dynamics and climate patterns. Monitoring auroras allows scientists to study the complexities of magnetospheric processes. Observations can unravel the mysteries surrounding magnetic reconnection events, where magnetic field lines realign and release energy. Such insights contribute to the broader knowledge of space weather, which poses risks to satellites and technology on Earth and regions where auroras are frequent. Data collection has become a routine part of research endeavors. Ground-based observatories and satellite missions collaborate to capture the nuances of these events, measuring variations in light emissions and particle fluxes. This comprehensive approach enables scientists to build models that predict auroral activity and its relation to solar cycles. The systematic study of auroras also sheds light on the atmospheres of other celestial bodies. Understanding these interactions aids in comprehending planetary evolution and habitability, making auroras a focal point in the quest to explore the cosmos. Capturing the essence of the aurora transforms mere observation into a profound experience. Witnessing the undulating waves of light across the night sky elicits a deep connection between the observer and the cosmos. This phenomenon, shaped by the solar wind, invites stories that weave together science, culture, and personal reflection. The vibrant colors, ranging from greens to reds and purples, inspire narratives steeped in wonder and tradition. In many cultures, these lights have been interpreted as messages from the divine or manifestations of deities engaging with the earthly realm. They have served as navigational aids and symbols of change, illuminating the dark skies of countless generations. The aurora's unpredictable nature fosters a sense of reverence, prompting individuals to share tales of encounters with this celestial display, often emphasizing the emotional impact of witnessing such beauty. Documenting these experiences enhances understanding, encouraging a sense of community among observers. Photographs and videos capture the ephemeral quality of the lights, allowing those who have not witnessed them firsthand to engage with the phenomenon. This collective storytelling nurtures a shared appreciation for the aurora, deepening humanity's connection to the universe. Each account echoes a desire to explore, to understand, and to celebrate the vastness that surrounds. Current limitations in aurora research stem from various factors, including technological constraints and the complexities of atmospheric interactions. Observations often rely on ground-based monitoring stations, which can only capture a limited perspective of these luminous displays. Satellite technology has improved data collection, yet the vastness of the auroral zone presents challenges in achieving comprehensive coverage, and this region's dynamic nature requires precise measurements of solar wind activity, magnetic field fluctuations, and atmospheric conditions. Instruments designed to capture these variables are often hindered by budget constraints and the logistics of remote deployment. The delicate balance between capturing real-time data and processing it for scientific inquiry further complicates efforts to understand the aurora's underlying mechanisms. Models attempting to simulate auroral phenomena depend on incomplete datasets, leading to uncertainties in predictions. Seasonal variations and the influence of solar cycles introduce additional layers of complexity, making it difficult to establish consistent patterns. Researchers often grapple with the variability inherent in these luminous events, as each display is unique and influenced by myriad factors. Despite these challenges, collaboration among scientists across disciplines fosters innovative approaches to auroral research. Improved computational methods and enhanced instrumentation promise to refine our understanding, gradually illuminating the intricate relationships between solar activity and the Earth's atmosphere. Insights gained from ongoing studies may illuminate the relationship between scientific exploration and public engagement regarding auroras. This phenomenon captures the imagination, drawing the interest of both researchers and the general populace. Curiosity about the interplay of solar wind and Earth's magnetic field fosters a unique connection, bridging the gap between complex scientific principles and accessible experiences. Educational initiatives often highlight the role of citizen science, where enthusiasts contribute to data collection and observation. These efforts not only enhance understanding, but also cultivate a sense of community around atmospheric sciences. The shared excitement surrounding auroras can inspire budding scientists, prompting them to pursue careers in astrophysics or related fields. Public exhibits and outreach programs further facilitate this engagement. Through interactive displays and informative lectures, they demystify the auroral process, breaking down intricate concepts into digestible segments. Such initiatives encourage a broader appreciation for the natural world, emphasizing the significance of atmospheric phenomena in understanding our planet's environment. The role of social media cannot be understated. Platforms allow individuals to share sightings and photographs in real time, creating a global dialogue. As these interactions unfold, the scientific community benefits from diverse perspectives, enriching the study of auroras and enhancing public awareness of the universe's wonders. This symbiotic relationship continues to evolve, shaping our understanding of both the auroras and their impact on society. The role of popular media in shaping perceptions surrounding the auroras is significant. Films, documentaries, and social media platforms have played a crucial part in bringing this phenomenon to a wider audience. Visual depictions often emphasize vibrant colors and sweeping formations, creating an allure that captivates viewers. These portrayals can lead to heightened expectations among those who seek to witness them firsthand. Travel blogs and online forums contribute to the narrative, sharing personal experiences of witnessing the lights. This exchange fosters a community where shared anticipation builds excitement. Such engagement often leads to increased tourism in regions renowned for their auroral displays. The economic implications are notable, with local businesses benefiting from the influx of visitors drawn by the promise of witnessing a natural spectacle. In contrast, the scientific intricacies behind auroras are frequently overshadowed by romanticized imagery. While the captivating visuals are undeniably compelling, the underlying physics remains complex and are, at times, underrepresented in mainstream portrayals. The interplay between the solar wind and Earth's magnetic field is a nuanced process, influencing the colors and patterns observed. While popular media can spark fascination, it also presents a simplified view, impacting public perception and understanding. This tension between spectacle and science continues to shape the ongoing dialogue about these mesmerizing lights. The legacy of Aurora research has significantly advanced our understanding of atmospheric and space sciences. These phenomena, driven by interactions between solar wind and Earth's magnetic field, have been meticulously studied since ancient times. Early observations laid the groundwork for modern scientific inquiry, instigating curiosity about the dynamics of charged particles and their behavior in different altitudes. Ground-based observations and satellite missions have provided invaluable data. Researchers have catalogued auroral activity, linking it to solar cycles and geomagnetic storms. This relationship has been critical for predicting space weather events, which can disrupt communications and power grids. As scientists have honed their techniques, they have identified distinct auroral arcs and structures, each revealing complex interactions within this region of the atmosphere. In addition to enhancing our comprehension of Earth's magnetic field, studies of the aurora have implications for other planetary bodies. Missions to Mars and Jupiter have unveiled similar phenomena, prompting questions about the universality of these processes across the solar system. It has become evident that understanding auroras enriches not only our knowledge of Earth's environment, but also our perspective on planetary atmospheres at large. The continued exploration of these lights serves as a testament to the relentless pursuit of knowledge, bridging cultural fascination and scientific inquiry in an ever-expanding universe. Whilst auroras are frequent, the data collection has become a routine part of research endeavors. Our liking for these have past a mystery that captivates both researchers and enthusiasts alike. This phenomenon, arising from the interaction of charged particles with a planet's magnetic field, illustrates the dynamic interplay between solar activity and atmospheric conditions. Each display is unique, influenced by factors such as solar wind intensity and geomagnetic disturbances, producing an array of colors and patterns that shift and evolve across the night sky. These luminous displays invite contemplation about the nature of our universe. They serve as a reminder of the intricate connections between celestial bodies and their atmospheres. While significant advancements in technology and understanding have been made, many aspects of auroral behavior remain elusive. The study of these phenomena continues to unravel layers of complexity, revealing the subtle nuances of electromagnetic interactions and atmospheric responses. Such beauty, coupled with the enduring enigma surrounding auroras, has inspired countless cultures throughout history. Their presence in folklore and mythology underscores humanity's deep-seated desire to comprehend the cosmos. Each observation fuels curiosity, prompting further investigation into the solar wind's impacts, not only on Earth, but also on distant worlds. As research progresses, the pursuit of knowledge regarding auroras will likely lead to new discoveries, enriching our understanding of both our planet and the universe beyond.